Thanks, Michael, for inviting me. I'm pleased to talk here. I think, I hope you will find this interesting. It's been a challenge to talk about Mellanox research challenges in the area of networks because there are so many that I had to pick up what I want to talk about. So I'll talk a little bit about Mellanox. I'll talk about how Mellanox conducts research and why we do that. And I'm going to talk about the challenges, the ongoing challenges, the ongoing work we have done. So, of course, some words on Mellanox. Mellanox is thriving on the fact that the world is actually getting more and more data and more devices that generate data. And it's been a challenge for the industry in general and the academic also to deal with that. And we see exponential growth in the amount of data available today in the world. We see a lot of new markets, new applications that actually strive on this data and use this data. And the data has become so big and we get so used to access it that the challenge is how to provide parallel applications that are able to chew this data and access it in reasonable power and reasonable time. And people are actually, because we have so much data, they develop ideas for how to deal with it in a ubiquitous manner and store it. And this world of data is actually growing very, very rapidly. What this actually means is that we need higher speeds to access the data because there is so much of it. And we need faster parallel processing to be able to crunch these huge amounts of data. And we also need better data security, following the theme of this workshop, to deal with this stored data. But I'm not going to talk about that. In general, Mellanox is a vertical market company. Let's start from the bottom. We do cables that allow people to build data centers. These cables are mostly optics, and what you see are different types of transceivers that we provide. And I'm not going to go through all the details about those. But on top of that, silicon photonics transceivers that we build, we also have, of course, we started as an IC company. We design our own chips, manufacturing them in Taiwan, most of them. And basically, we provide NICs, we provide switches. Now we provide network processors after acquisition of EasyChip last year. So what we do with these ICs, sometimes we sell them as devices, but many times we make systems out of those. We sell network interface cards. Today we sell up to 100 gigabit per second interfaces, both in InfiniBand and Ethernet. And we have switch systems that we provide at the same range of communication, very low latency. And then we also have some products that deal with how to connect distant InfiniBand clusters. We call them Metro X. And with the new acquisition, we also provide MPUs that are marketed both at the device level and the card and the system level. And one thing that I want to emphasize, we already provide a multi-core processing power integrated with the NIC. It's a product that is called Bluefield, and some of you already heard about it. So on top of all that, there is a layer of software, of course, to make something useful out of all that hardware. And we provide from the switch operating system we call Mellanox OS. We provide management software for InfiniBand clusters, for HPC clusters. We provide accelerator software called VMA, allowing you to build user-level communication stacks on top of VMA. People use it to accelerate applications like machine learning, or now we have a huge project on streaming, allowing streaming high-definition video in large amounts over VMA, which allows you to accelerate up to the application level. HPCX is our HPC software, and Neo is another management tool. So until now, it was Mellanox marketing speaking. Now let's talk about my topic. So as I've shown you, Mellanox is a pretty vertical in its disciplines. And what I'm showing here is the way I look at it. We have engineering at multiple levels, multiple disciplines. And the fact that we're able to create a full graph, a nice connectivity between these disciplines is the strength of the company. Without this kind of graph, you cannot make state-of-the-art devices and equipment and algorithms. So you can see a VLSI, of course, we make chips and systems and software, but interestingly enough, we have quite interesting challenges in the product engineering domain, where you actually roll out these devices. They have to be qualified in a very efficient manner. So product engineering is a field where you apply engineering to verify your devices. In the interconnect, we name interconnect all our cabling business, the silicon photonics. Mellanox acquired Cotura, which was a very famous silicon photonics fab in the Los Angeles area. So it's been a while since then. And they provide us the ability to do these transceivers. Operations is also interesting. Once you start selling hundreds of thousands of entities of products in a year, you actually need to manage that to build efficiency, to build cost reduction schemes. So we apply engineering to that field also. So with this diversity comes the question, how can you have these organizations and build excellence and make sure that you are at the edge of the technology all the time? So we realize that we have to utilize research methods, similar to academic research methods, how to track the knowledge in the world, how to track the important conferences. So we incorporate these methods in a way that lets us stay at the top of things, at the front of the technology in all these fields. So one way to do that, and this is the way most companies do, is they create a standalone research group. And we decided it's not a good idea for Mellanox to do that. Because once you have a separate research group, you suddenly have a barrier. And people wrote papers on technology maturity model, for example. How to transfer technology from this research group to the core group. So for Mellanox, we decided we are going to implement this research done in a different manner. We are going to have a research network. And research network means that there's in every one of these organizations, there are researchers that are organic part of the group. So they are very tied to the products of the system or of the company. And these researchers are now applying research methodology that makes them work in a network. So they're connected to each other. So that's the way we do it. Of course, selling to the hyperscale guys, we are now talking about networking. So selling to the hyperscale guys expose us and let us work with the hyperscale research groups. For example, I can talk about Microsoft Research. We published with them, so it's very evident we work with them. Yes?
So in general, would you say that having a separate research group, Microsoft Research, VMware?
Well, maybe they are big enough organization to do that. Mellanox is only 3,000 people, so we don't do it. But in general, from my experience, for example, I worked in research group in Intel in the 97 to 98. 2 years. They had the same problem. I mean, I was working on CAD research, and we invented stuff that eventually most of it was not accepted. So if you work from within the organization, it's easier. The technology maturity model is easier to pass. So that's a philosophical question. Where do you want to conduct research, and how do we apply the network so people can say that we don't apply enough methodology to our research. But let's focus on the topic of today. So we have research in machine learning and application acceleration. We have research, so that's mostly software and how to use the hardware in an efficient manner. We have networks research I'm going to talk about. We have CAD research, mostly informal model checking, but not only. And silicon photonics, of course, we also have a fab, so it's quite deep in the physics. And even on operational, how to conduct efficient operations in a company, it's not a trivial thing. So I was involved in one of these projects. We dealt with the question, how and what can you do if you know exactly each piece of equipment that you sold, what was the origin of that equipment, from the manufacturing week of every capacitor and resistor up to the assembly house, to the testing that you did. What can you do with that, and what kind of gain you can make? So this is really a research question we dealt with. Actually, we found that some French group dealt with similar questions in the past. Anyway, so let's focus networks, okay? Because I don't have a day to talk about what we do. So we established network research a few years back. We work on a lot of these papers, but in a 3 years period, we published 11 papers. But consider the fact that it's not our task to create papers. The way we work is that we have to promote Mellanox business. If there's a reason to create a paper about something, to tell somebody what we have done, we will do that. But all these papers are driven by some market demands. So we probably have the same amount of work that we did and we never publish. So I'm not going to be talking on these topics, but just an example for stuff we did. So what I want to be spending a few minutes on is this. So I focus on the network research, and I try to put here some of the active topics that we deal with. You can see it's very wide in its cover. So for example, we deal with topologies, and we have here Simon that deals with expander graphs. And of course, if we can hire him for this summer, it's still a matter of law and getting the permission to hire him. But if we can do that, then it's going to be the summer of the expander graph research in Mellanox, and we want to be able to show that given the current hardware, or find out if we are lacking something in the current hardware, is maybe even more important, that will allow us to actually provide adaptive routing and static routing for expander graphs. But in general, we study topologies in general. So I have personally studied topologies of fat trees quite some time. So the next item I'm going to talk about is about flexible hardware congestion control. So congestion control in general is a networking issue for many, many years. I mean, clearly, if we can do something about congestion control in the hardware, we are going to gain a lot. We are going to gain the speed, because whenever you have to go to software to deal with congestion control, you are going to spend context switch in a kernel thread. So can we do something in the hardware that will be faster? And of course, more scalable, because if we put some stuff in the hardware, we believe we can scale out to much larger number of flows. But this new problem here that I quote you, 2 papers from last year, SIGCOMM, the problem of unfairness caused by mixing of TCP flavors in a cloud is something that we believe we can solve. If we do the congestion control in the hardware, it's going to be transparent to the VM what the congestion control is, and by that we solve this problem. So we have a lot of reasons why we want to do hardware congestion control for TCP and for Rocky, of course. For Rocky, we already have that, but for TCP, for example. So, of course, the challenge is clear. People worked on congestion control for TCP for maybe 40 years or something like that. And they cannot agree on the algorithm. I mean, every year we get new ideas and people claim that's better. And so if I implement an algorithm in hardware, it's very hard to change it once the device is out. So how can we resolve this problem? So this is really the core of this research, how to resolve this problem. Enable flexibility in programming without breaking the cost of the device. Because solutions like going to embedded FPGA, we already discussed them, they are pretty expensive. So we need something better. And FPGA will not work at the speed that we want to work at. So anyway, this is an active research, and let's go to another one. Okay. So I don't have time to go over all of them. What I propose is if you find here some item that you want to talk about in depth, then let's try and talk to me. If I have time, you can ask, but I guess I will not have leftovers. So let's talk about it offline. So I'll talk about another topic. Basically, a Dragonfly network, we didn't invent it. It came from Dali's group. It's a two-level topology. Basically, if you look at it from terms of graph theory, you would say that you split the vertex of the graph into groups, equally sized groups, and then you at the top level, if you look on the partitioning of the graph edges into these groups, you will find that they are cross-connected evenly with in a shape of a full graph. So think about it this way: you have a graph. And once you split it into groups of vertices, between these groups there's full connection with the same amount of bandwidth. Now, Mellanox introduced something we call Dragonfly Plus, which is an implementation, a proposal we published a paper about this, the benefits, so I'm not going to talk about it. But there is a reason why we want to go to internal to this group, to this partition. We want to have a full bipartite. And the connections to the global, in the global graph, are going to be provided only by the top switches in this topology for some reason. And suddenly we have a degree of freedom in the way we connect these connections to all these top-level switches. So we have a degree of freedom. And the question is, what's a good connection? From performance perspective, but also from cost perspective. When we look on the cost of such network, surprisingly, to me at the beginning, was that the cost of the cables, the long cables, the optical cables, is roughly, a cable cost is roughly the cost of the ports on the two switches that it connects. So it's fairly not negligible. I mean, if you buy a switch and you buy another switch and you connect these switches, then the cost of the cabling will be the same as the cost of the switches. So it's very expensive. So if you look on this topology, the way it's being drawn, and you have these switches connected together in what we call a group, then if you look at it, you will figure out that the Tor connection is going to be a short cable, which is for free. It's a copper cable. But these long cables are pretty expensive. Yes, Ankit?
Very quick clarification. When you say cost of cable, are you including the transceivers?
Yes, of course. Of course.
No, you could account for them at the Tor port or at the cable, right?
Okay, so we count them on the cable. So,
but you said that the short cables are basically free. So you said so basically transceivers are.
Yeah, these are copper cables. Less than 3 meters, you can do copper cables. Okay. Depends on the speed, but I'm talking about 100 gigabit per second. It's about 3 meters. Mm-hmm. So these will be very, very cheap, and these are long, and you have double the number. So the number of cables at this level will be equal to the number of hosts. Depends on your bisectional bandwidth, but normally, that's the way it's being built, and here we have only half.
So the hosts are connected via 100 gigabit to the
Yes, yes, in this case. So the question is, what can we do to reduce the cost? So actually, we figured out that if we use the degree of freedom for how to connect these cables, and we are connecting, for example, all the number 1 switches to each other and creating cliques of connection, we can do a simple trick and place them, all the cliques, close to each other. So suddenly, the long cable that used to connect these switches to each other becomes a very short cable. So this is nice. I can show it for this topology, for this number of ports, this number of groups. But it's clear, and we know that there are some other numbers of groups or other number of ports where this cannot be done. Yes.
So some cables became shorter, but some cables became longer, right? For example,
So these cables became a little longer, but the cost of the cable is not the cost of the length; it's the cost of the transceivers. So the length of the cable is it's not negligible, but
for that, for the cable connecting the one in pod 21, to the right.
This one?
Yeah, that one to that upper.
No, physically on a floor plan, these racks are placed in the middle of the data center. So the distance is the same. I'm just drawing it flat. I mean,
So this comes with some physical data.
yeah, of course, but critically, we saved third of the cost of the cabling, which is 1/6 of the cost of the network, doing this trick. So
So if the length of the cable is not really the cost, then you have to buy like more expensive transceiver. What's the cost? Like,
No,
what's-
going
If you
from-
need to go optical, you need to put the electronics at the end of the cable.
right.
If you don't, you don't. So up to a certain length, you're in copper, plain, just
That's fine.
beyond that,
beyond that, you pay for the transceivers, and the transceivers don't care if it's 100 meter or 30 meter. Okay?
Okay, so basically you're replacing those with copper and network.
Yes, that's copper.
Okay.
So we saved a lot. So we have a research question. We know we can do that for particular sizes, for particular numbers. First, we ask ourselves, what will be the number sets that will allow us to do it? Second, we ask ourselves, if we cannot do this trick perfectly, can we still have something that is close to a click partitioning, where the cost, we minimize the cost of cables that cross these connections? Maybe we can do that, so it's not optimal like the way I draw it here, but it still gives us a lot of saving. So we have done sub-optimization. We implemented simulated annealing, and we see that this problem looks like it is actually convex problem for optimization, but we don't have the proof. So we're working on this topic. I'm running out of time, so I'm sorry. I'll have to be quick here. So I'm just teasing you. I mean, each one of these topics is deep. I mean, it's much deeper than the way I described it. So the last thing I want to do is to dive in. I mean, I've stayed in a fluffy layer until now. So let's try and say something reasonable about some of these topics. And let's talk about optical data centers. So in optical data center research, actually, we are sharing with Michael work under the Israeli chief scientist in a magnet. It's a consortium named Petacloud, but what I'll be showing you mostly is what we have done through the nefeli project, which is a 2020 Horizon 2020 program in Europe. So we focus on three different aspects of the problem. The first one, are there any fundamental limits? And I'm trying to, under Petacloud, to work on this topic with Tzachi Birk, Professor Birk, that sits here. So fundamental limitations, analyze them, figure out what can be done, what does it say on the architecture. Now, talking about topologies, of course, there is always the question, what's the best topology and what can you do and what you can't do? And then talk about the actual circuit scheduling, and I'll go through what it means in a few seconds. So why do we want to work on optical data centers? That's my boss asks me, why do you waste your time on optical data centers? People worked on it for so long, and optical burst switching has been there for, I don't know, 40 years maybe. I don't remember when it started, but people tried to do stuff like that in the past. So why are you working on it? So our first work was to figure out the reason. So people claim, it's not my claim, as you will see in a second, that you can actually save a lot of power by reducing the number of translations from electrical to optical. Once you go on the optical network, you stay optical until you leave the network. It sounds reasonable. If you look on Google's paper about Jupiter Rising, I'm using their drawing, a 3-level FET tree, you have 6 cables you have to cross, and so you have 6 if these are electrical switches, you have to go from optical to electrical, and then leaving the switch, you go electrical to optical, so you have 6 transitions. I'm quoting here a power number, which is the target power number for a single electrical to electrical, which is the target. Nobody has reached there. I think the best people got was about 3 picojoule per bit, but actually, let's use a number of 10. So I'm changing a little bit this foil. Let's assume it's 10, so we get half a watt per interface. So if I'm saving all these 5 extra conversions, because I go once to optical, then I leave and do once from optical to electrical, then I saved 5 such translations, and I saved 5 watts per host, per pair. Okay, so this sounds a lot, because I have 10,000 pairs or something like that. Well, if you look on the power of a data center, this is nothing. I mean, every host today, modern hosts utilize GPUs and they use quad cores or more than that, and 500 watts per host, I mean, is something that people talk about. So this is not a good reason to go to optical. So what else? Now, I'm quoting a graph from the same paper showing the exponential growth of demand of the bandwidths that Google need in their data centers, the aggregate bandwidths. And now comes the real question, what we can reach with silicon switches. So until now, there is no evidence that we cannot scale our switches. I mean, we are building a 200 gigabit per second switch today. We don't see the ceiling. I mean, but if you look on silicon technology, let's go to academia for a second, and we look on silicon scaling. How do you scale silicon technologies? And you find out that silicon technology scales from one generation to the other, reducing the power density, I mean the power per node, the power per single connection within the chip is going to scale by several tens of percentage. So let's say 20%, 30%. But if we want to exponentially grow the bandwidths supported by this, oh, and another thing that silicon technology doesn't do, it doesn't change the frequency. When I started doing VLSI, every year we would double up the bandwidths of our chip. I mean, it was no problem. We started with, I remember, maybe 10 megahertz per clock, and next year it was 20 megahertz, then it was 40 megahertz. And so we got very fast frequency, but that stopped in 1998 or something. So we need to have more aggregate bandwidths. We cannot change the frequency, so we will probably need double the number of nodes. So if we double the number of nodes and we didn't have less than 50% scaling of the power density, we are going to explode in power. And that's the main risk, and that's the main reason I'm working in optical data centers. It's not clear if that's going to happen, but there are some signs for it. And the next slide is going to show you the main sign for me. So ITRs is a global organization that deals with prediction of the silicon technology for maybe 40 years, maybe more. All the big silicon IDMs, I mean the independent fabs in the world are contributing to this effort for so many years. So they provide predictions, and the last few years they used to provide predictions at the level of the silicon technology. In the last few years, they formed ITRs 2.0, which is an organization that looks on the system aspects. So they try to translate the silicon technology predictions into system predictions. Yes?
So in your vision of optics, is it the rack switch that's becoming optical itself, or are those ports
I'm not going
still-
to answer that. You will figure out yourself. So if you look on ITRs, this is a report from 2015. It's pretty recent on data center technology. So I encourage you to read the reports. They're pretty interesting. So if you look on their prediction, they predict exponential growth in bisectional bandwidths of the data center. That's the blue line. It's a nice line. It's given in terabytes per second. Now, if you look on the other hand, you look on the switch bandwidth prediction. Now it's given in gigabytes per second, and you can see a flat. So how can it be? And in 2025, they predict a 4x more bandwidth for the switch. Now, if you read the report, it's evident they are talking about optical switching. So actually, I have more evidence for people, very smart people, and we have the technology development of Intel, technology development of IBM, the global foundries, everybody that does silicon technology is here. So that's what they predict, so we may have a problem. So this is why I'm working on it. Okay, so I gave you the motivation, and I'm running out of time. So what's the main difference between packet switching, what I will call electrical or Ethernet data centers, to optical switching? The main difference is that for optics, we don't have buffers. There are some claims that people can take some fiber, very long fiber, and of course, you cannot pack it into the size that you need. But let's take a very long fiber, a few kilometers of fiber, and then you use them as a ring. So you can take the right light and turn it around. But it's very, very limited. You cannot keep it forever. I mean, it's destroyed by itself pretty fast, and it's very costful. And you don't have enough buffers. You can have one single packet buffer maybe. So you cannot, if you don't have buffers, what it means that if you could stop a packet in the buffer for a while until the output freeze in the electrical switches, you can't do that for opticals. So once the packets enter the crossroad, they're going to collide and dead, and they are dead.
Well, maybe this solves your deadlock problem.
Yes. There is no lossless network in the, yes, it solves some of the problems. So that's the main problem, and the result of this problem is that people actually, when they talk about optical switching, they are not talking about packet switching. They are talking about circuit switching. So they build a circuit from a source to destination such that it is guaranteed that the circuits are orthogonal. Now, when we talk about circuits, the modern optical data centers talk about not only about physical fiber, they talk about separation in color, separation in mode, and separation in angular momentum. But still, there are circuits. Once you have this triplet of link, color, and angular momentum, or actually, I don't know of anybody that is doing it in a quadlet. But anyway, so they are forming circuits and destroying circuits. And this is a major challenge for optical data centers. So,
aren't they actually mixed? Because if you assume that the optics doesn't start from the port of the computer descending, but rather from the Tor switch, then actually when you look at it, it looks like packet switched, then an optical pop, and then again at the destination switch, again.
yeah, so I have to convert.
A combination of both.
Well, a single link from the host to the Tor, I don't consider it an electrical switch. And you will see. I'll talk to that. Some architectures suggest that having few levels of electrical, then go to optical, then few levels of electrical. But I'm not talking about it. Of course, I cannot provide all the vast possible architectures people invested time to research in my simple 40-minute talk. But people also work on something they call distributed or optical packet switching. There is a field of research that is called optical packet switching. And they are trying to make the switches smart enough such that the switch itself is non-blocking from the point of view of optical network. So the switch itself guarantees a low drop rate, okay, very low. But nobody, and to my best knowledge, nobody has shown that end-to-end, if you have multiple levels of these switches, which is a question how you build these switches, they use lambda translations normally, but which is there's a physical, you have to show that it's doable in high count. But nobody has done that. But even if you are able to show one switch that is operating nicely, and there is very nice theory about elastic packet switching in optics, very interesting papers from a group from Poland that I really like. But still, at a system level, nobody has shown a reasonable drop rate when you have multiple levels of these switches, that because they are not synchronized in any manner. So what I'll be talking about, and what I think the world is focusing on, is an SDN view of optical data center. That's the main research. And most of the research does not claim that you can build this and have a full, what is called all optical network. They always work on hybrid model where part of the traffic will go on an electrical model, or electrical network, and the high bandwidth part will go on the optical network. So I'll be focusing on that. If you consider this model, then you could actually foresee that there are, let's say that we want a system that is able to react to the current demand. So you can foresee several phases of the operation of this network. Question, Michael? You asking something?
Oh,
No.
Yes, but I didn't raise my hand.
Okay. Okay. So.
But I will ask. So the first one, the collecting demands one.
Yes.
Is that the main challenge?
I'll get to it.
Okay.
I'm just trying slowly to get to say something meaningful. So if you look on the phases that are required for this central controller to provide commands for building and destroying circuits, you will see First, we have to collect the demand matrix, what we'll call the traffic matrix. Then we'll have to allocate resources. That's a scheduling phase. Then we have to deliver that schedule to all these elements. Don't forget, we are talking about large networks. There's no point in producing 100 Tor network. Nobody is going to use it. We are talking about at least 1,000 Tors, okay? At least, if not 10,000 Tors. So, depends who you ask. So, you have to deliver that configuration. Then the switch, the physical switch, the optical switch has to adjust to the new commands. Then you can actually send traffic. So, of course, I'm electrical engineer, so in my background. So, you do pipelining, of course. But in a pipelining theory, the worst pipe stage is going to dictate your throughput, what you can do. So, oops. So let's talk about fundamental limitations. It looks like I'm not going to be able to pass the fundamental limitation stage. But the first fundamental limitation is collecting what you were asking about, yes? Collecting the demand matrix. Let's say that we have 1,000 Tors. Then each one of these Tors, the matrix size is going to be this n square. And let's assume we need 2 bytes to maintain this data, that we are already at about 2 megabytes of data that we need to collect. Now, let's assume we collect that 2 megabytes per data on a 100 gigabit per second link that is connecting the scheduler to the network. Then the best we can get is 160 microseconds to collect all its traffic matrix. So people are working on ways to improve on that. I'm working on ways to improve on that. There are some interesting papers on the pipe, but still, it's one of the fundamental limitations. If your traffic matrix changes dramatically from one sampling, from one pipe to the other scheduling pipe, then that's your limitation.
I mean, even if it changes, the end-to-end RTT in the network would be something similar, a few hundred microseconds. Congestion control cannot react faster than a few RTTs, so it doesn't make sense to
Okay,
demand.
I'll try to answer that.
Then the response of the congestion control.
I'll try to answer that later. Okay, there are different. Of course, the congestion control is another topic I'm not talking about, but still, people have worked on it. If you read see-through, they have talked about TCP in this field. And anyway, so next fundamental issue. Yes.
So regarding the first, are you actually collecting demands, or are you just figuring out whether A is talking to B
Byte
now?
Ah.
They're doing byte count, I think.
So there are different.
Current.
So Michael, there are different ways to do that. All I'm saying, no matter how you got this information, it has to reach the central scheduler for it to do a schedule, a valid schedule. And that's by itself a problem.
Yes, so I understand why this is a lower bound on how fast you can react. I'm just wondering if underlying this is the assumption that flows persist long enough and that you realize
No,
enough
you need to
till you can start
without that
collecting.
you cannot
Divide it
function.
by flow length, and then you'll get the real.
So I don't have any assumption like that.
Aggregate, I think they assume that there's enough step maximum on a short time scale, so that's such that the aggregate is stable. I think that's my assumption.
So-
That's the assumption.
So I don't think there is, in what I'm presenting here, there is no such assumption. When you build a system, you have to take more assumptions into account. How do you do that? I'll try to get to it. Maybe you will let me steal a few more minutes because I don't get to the actual stuff.
You should ask Brighton.
So another fundamental limitation that I'm bothered with is the configuration space that is required to configure these switches. So I'm not going to go through the details because I don't have time, but actually you will see that there is a significant amount of data that is required. If you want to change drastically the configuration of the network from one slot to the other slot, it may take you a long time. Just because you have to send a lot of data out. And you may have a lot of these switches in your network. So that's by itself is a limitation of this architecture as I'm drawing it. And now we also surveyed other different questions. For example, the latency it takes to reach the destination, which is not a problem. And then we studied time synchronization that is needed to synchronize all these operations, which is not a problem. And we also surveyed, actually we didn't do this research, we just found that people are working on the problem of burst receiver. The problem is that Unlike in Ethernet data center, you have two switches connected to each other, then the modulation of the data on the link is done by one switch all the time. Now, on optical data center, your source of data is going to change when you create new circuits. Every new circuit you created, you have a new source, and that is going to create the fact that you have to recover the modulation frequency of the different source in very fast manner. So luckily, we are not the first ones to deal with this problem. Passive optical networks already spend years on solving this problem, and there are very nice numbers like 41 nanoseconds to lock, 25 gigabit per second.
Apart from the delays, what about consistency and stability when you do these changes in the network?
Stability from the point of view
From
of
the
network
point of view-
stability?
Yes, because I mean, you change circuits, but what if you change here, but you don't?
So the stability has to do with our ability to schedule the traffic onto the network and make sure that no buffers are exploding. There are no buffers in the network. The buffers are on the host, so we have, or in the TORs. So yes, of course, scheduling algorithms that we will need to deal with have to prove stability over time.
I mean, the transitory state after you calculate and you want to update the switches.
So I'll try to answer it later because I don't have time. I'm not sure I follow your question. So I will not go through the details of, I plan to spend some time talking about this project. Mellanox is involved in a project called nefeli. As I said, the idea behind this project was to actually be able to build an optical data center with custom off-the-shelf equipment. And to learn from this experiment, my target in this project was to learn from this experiment all the problems I talked about before, to find out what are the bottlenecks in this architecture, and what we have these partners, 4 industrial partners, Interroute our provider for one equipment and one connectivity. Nextwork are experts in SDN engines, whatever, SDN controllers and OpenStack, etc. Seagate and ourselves are hardware manufacturers. And then we have 3 different research organizations joining this project. Basically, we built a system that is based on the regular hierarchy in the data center. And we chose to do time-slotted scheduling. I mean, we plan for the future. Who is going to talk with who, when. And then we use OpenStack and OpenDaylight for implementing that stuff. So you'll forgive me for skimming through these details. Of course, scheduler is getting a traffic matrix, and it needs to provide a set of permutation matrices, but it's not a simple permutation matrices. You can see there are other constraints imposed by the topology that we use, so it's a challenge. We actually spent a lot of effort in this project to try and solve the scheduling problem. If you apply the optimal scheduling, we are, even for 1,000, for this size of cluster, you are talking about tens of seconds. If once you get a sparse matrix, a dense matrix of demands, and close to full bisection requirement of the network, you are in a problem to use partitioning a traffic matrix into orthogonal permutation matrices is very expensive. So we examined multiple heuristics, but all in all, the offline algorithms that we used were pretty bad. We never crossed, I think, less than a second on real loaded network. Now we also looked on incremental algorithm. An incremental algorithm actually allows us to utilize previous traffic matrices to build the next one. So we do a diff analysis of what changed and etc. But this suffers from the fact that we sort of assume that the traffic is sort of has this long-lived behavior, which is a big question. And to summarize this work, so this is the software elements, and to summarize this talk about optical data centers, I would say that we recognize that today the device that you cannot purchase that was required for our topology, for our implementation, was the WSS, it's called a wavelength selective switch. It gave us configuration time. The fastest we could find was 10 microseconds. This actually dictated that our slot time, the full configuration of a permutation, is going to be about 200 microseconds, which is very, very slow compared to what I want to get. I want to get to a few microseconds, not, this is, in my perspective, at least one order of magnitude more than making this kind of architecture feasible. So, to your question about latencies and RTTs and how do you deal with it, of course. So, this actually is a big question. I mean, we need to break this barrier to make something useful. The full worst case schedule for an all-to-all traffic will be 80 such schedules.
What does that mean? That's how much you have to wait until your packet gets through?
Yes. Today, 16 milliseconds for the worst case all-to-all traffic, that's what the amount of time you will have to wait, which, of course, is a challenge for any congestion control algorithm. But we didn't spend the time tweaking TCP to make it work best here, okay? In our demonstration, we'll be using UDP. But that's, okay. But the big drill in research, and that's what makes it research project, is that you are not bound to delivering a system. You are bound to learn. You are bound to figure out what are the bottlenecks, what are the critical things in the architecture that you have to change to make a product. So that's what we did. We also figured out there is another bottleneck that we didn't think about before, which is SDN controllers. The speed of SDN controller is just to collect the traffic. Forget about the limit that I showed you, the fundamental limit. It was at least 3 orders of magnitude worse than a fundamental limit. And then a full configuration of the switches was 2 orders of magnitude worse than what we expected, even though we tried to use incremental. So it was a nightmare to get anything done, and actually we couldn't. I mean, the system is much slower than these numbers because of the limitation in control. And of course, scheduling is a huge challenge. Of course, people work on all these problems today. This is just one way to look at it, being practical. There's a lot of research in the world, and I encourage you to look at it. It's very interesting. So to summarize my talk, we believe in Mellanox that the activity of the research group is key to keep us at the edge of the technology. It's something that we invest a lot of time in, and we do it in a different manner than most other companies. We try to keep the researchers integrated within the architecture group or in the software group, and we have some member of the group here, Chagai, and so I'm happy I was able to show you that. Thank you.